All right. Good morning, everyone. Thank you so much for joining us. Today we have Kian Salimkhani from Radbound University. He did his PhD at the University of Bonn, after which he did studies at the University of Oslo and the University of Cologne. He focuses on metaphysics, methodology, and fundamental questions in physics. And today he's going to tell us about non-fundamentality of space-time from the perspective of philosophy of physics. Thank you so much for being here with us, Kian. Um, we're excited to hear what you have to say, and for our guests, please feel free to throw questions into the chat and the Q&A. And we look forward to a great discussion. We'll probably take questions towards the end. Thank you so much. Take it away, Kian.
Thank you so much, Delilah. Very glad to be here, not in person, but remotely with you. So thanks very much for the invitation. The plan for today is basically giving some background to Niels Lindemann's talk from 2 weeks ago, I think, by presenting a version of the main argument of this book. I will first talk a bit about what fundamentality means, since we often use the notion without further clarification. Then I will basically sketch my main argument, or a certain way to present the main argument of this book. And towards the end, I will talk a bit about a few problems and caveats, which relates back to Niels's talk here in this seminar. So one disclaimer, I will not really present much of the physics here, but really give a philosophical interpretation of certain results. Just to warn you in a sense. So what is fundamentality? Physicists typically use the notion as a primitive concept that is hardly analyzed. So you can apply it to entities, equations, theories, and sometimes you analyze it further, then you find it typically understood in terms of a broad notion of composition, you could say. Alternatively, it can be related to the to a highest energy scale, more specifically in the sense of the cooling history of the universe. You will then get also a link to a sense of what is first in the sense. When we move to philosophy of physics, the situation is quite similar. There are a few exceptions, but fundamentality doesn't really receive much analytic attention from philosophers of physics either. This is very different from other notions like emergence, for example, where there's lots of debate and lots of explication going on. Again, we typically find a primitivist notion of fundamentality that conveys a minimal meaning of the term informed by how physicists use it. Seminal papers do not define the notion, and some seem rather skeptic and deliberately avoid the concept. Occasionally, however, philosophers of physics will explicate the concept of fundamentality, and then the fundamental entities are, for instance, those that are defined in the kinematically possible models of a theory, or that feature in almost all models of a theory, or almost all solutions of some relevant equation. Sometimes we can also read a more philosophical clarification, like, for example, self-standing and autonomous, ontologically distinct and primitive, or in fact, ontologically independent, which is one of the standard explications you find in contemporary analytic metaphysics. And then, and in metaphysics, the overall idea is that questions of fundamentality are really questions of ontology, in the sense of what grounds what. So the question whether some entity is fundamental is not merely a question of whether this entity is on the list of what there is, but about investigating its ontological status with respect to other entities, or with respect to with respect to other entities. I will come to the subtleties in a minute. So first of all, that means that we can distinguish these two ways of talking about fundamentality. We can distinguish between relative and absolute fundamentality. Entities can be more or less fundamental, and maybe some entities are absolutely fundamental. And there are then basically two different ways to understand the idea that fundamentals are ontologically privileged. And this can be motivated, for example, by thinking of what a fundamental entity or concept is in an explanation. In physics, we typically try to explain, so we can think of an explanation, and there the fundamental can be viewed as that which is unexplained itself. So the explanation stops at the fundamental entity or concept, doesn't go further, and that which does explanatory work itself, that which explains. So we can think of fundamentality in basically two ways. We can analyze the unexplained part, and we can analyze the explaining part. And the first is, in a sense, downward looking, and the second is upward looking. According to the downward looking aspect, the fundamentals are ontologically independent. And according to the upward looking aspect, the fundamentals are in the set of entities that determine everything else. Here's a way to understand, especially the second way of talking about fundamentality. According to the famous God metaphor, the fundamental entities are all and only those entities which God needs to create in order to make the world how it is. Okay, so we have these two notions of fundamentality. How do these two concepts, independence and determination, relate to each other? Often the assumption is that both concepts pick out the same notion, but there are cases, notably, where the concepts can also come apart, but I won't talk about them today. It's kind of also more towards the metaphysical debate. You could argue that maybe in physics you don't really find these examples. Maybe you do. What is more interesting, I think, and what I will talk a bit about now is that especially from this applied perspective of philosophy of science that uses these kind of metaphysical results, both concepts of fundamentality correspond to methodological practices in the philosophy of physics that run counter to each other. Fundamentality as independence is used when we investigate whether there is a reductive explanation of something. And fundamentality as determination, on the other hand, is used when we investigate if some entity is indispensable for explaining something else. On the independence view, one is essentially not accepting primitivity from alleged indispensability for some sort of explanation. And on the determination view, one refuses to give a reductive explanation in a sense. Now, if reductive explanations are feasible, a primitive and we kind of posit some entity as primitive, then certainly you will introduce a redundancy. You wouldn't need to put this in, but you did, so there's a redundancy. But it might even introduce an inconsistency for the following reason. The fundamentals are conceptualized as truly independent, that is, they do not depend on each other. This constrains what we can combine as fundamental. fundamentality as independence implies demanding some type of consistency. And that would mean that positing some entity may not be as innocent as it seems. Now you can turn this around. Say we look for inconsistencies in our theories of physics, or we look for unsatisfactory explanations or so. We can then interpret them as such unresolved tensions within the fundamental posits. In other words, hidden dependence relations among the allegedly independent posits of a theory can occasionally show up as theoretical inconsistencies. And in the book, I take positing quantum matter fields, the Heisenberg uncertainty principle, and continuous metric field as an example for such a case, where you can then see how certain inconsistencies in the theoretical framework can be related to issues of fundamentality. The main point being, again, we might think we posit something as fundamental, as independent, but there are actually dependencies that render the whole picture inconsistent. Okay, so for today, the key question is now whether spacetime is fundamental, that is, whether spacetime is ontologically independent. And first, I would just give two side notes on this. So on the one hand, the issue of fundamentality versus reality needs to be briefly addressed, I guess. So the traditional question in the philosophy of spacetime was about whether spacetime is part of our ontology, that is basically whether it's real. And nowadays, several philosophers have argued that it actually has always been about whether spacetime is part of the fundamental ontology, more specifically, and hence it is about fundamentality and not so much about reality. And crucially, when we talk about fundamentality rather than existence, we talk about, or you could say at least emphasize or make more explicit that we talk about dependence relations within the theory or within the domain we are considering. And I think this has several advantages. First, we understand the input from new theories of physics more appropriately. New theories do not just provide us an update about what there is, but they shed new light on various dependence relations. This attention to dependence relations also guards against the formalistic or literal interpretation of a theory, according to which we basically read off our ontology from what appears in the relevant equations. And lastly, in the spacetime case, two largely separate debates about relativity theory converge fruitfully when we focus on dependence relations. In light of recent work together with Rasmus Jørgsland, I would also like to state that the focus today is about metrical aspects of spacetime specifically. Okay, so here is the central claim we're considering now of spacetime metric fundamentalism. The metric field is fundamental, that is, it is ontologically independent. And in the following, I shall present now two ways of basically challenging this claim. And here's the first, which is due to Harvey Brown and Oliver Pooley and can be framed as the coincidence problem. As a matter of logic alone, they write, if one postulates spacetime structure as a self-standing autonomous element in one's theory, that is, as ontologically independent, it need have no constraining role on the form of the laws governing the rest of the theory's models. Brown basically asks what explains what. So what is geometry doing here? Codifying the behavior of free bodies in elegant mathematical language, or actually explaining it? Or at the heart of the whole business is the question whether the spacetime explanation of inertia is not an exercise in redundancy. It is non-trivial, of course, that inertia can be given a geometrical description, but what is at issue is the error of explanation. So after this criticism, the spacetime metric fundamentalist needs to add a second claim, basically, which is this chronogeometric requirement. So you have the first claim, the metric field is fundamental. The second claim is added. Material rods and clocks built from matter fields survey the metric field because the symmetry properties of matter fields, of the matter field dynamics coincide with the symmetry properties of the metric field. But then critics like Brown, for example, can say, well, either there is no explanation, it's a pure coincidence, or this is giving an implausible explanation. The metric determines matter field properties, which they deem implausible, or you have some kind of extrinsic dependence relation. It only works in virtue of something else, for example, the dynamical laws and equations of motion. And therefore, in contrast, the central claims of the dynamical approach, which is due to Brown and Pooley, are as follows. First of all, chronogeometricity is not a property that geometrical structures have intrinsically, that is in virtue of themselves, but in virtue of the dynamics of matter fields. And second, fixed background structures, such as the Minkowski metric in special relativity, are ontologically reducible to the dynamical symmetry properties of the matter fields that constitute physical bodies. And again, kind of chronogeometricity is the property of a field to act as a metric that is surveyed by rods and clocks built from matter fields. So the main idea of the dynamical approach here is to consider how we measure spatial and polar distances. Why do material rods and clocks measure spatial and polar distances? In other words, how does the metric acquire its chronogeometricity? And the proposal is that this is because rods and clocks are not independent, but built from these matter fields. And then, if you look at this, at this debate in this way of you talk about dependence relations and so on, then you can say that the metric field depends either partly or fully on the matter field content, on the matter field dynamics. In the partial case, you have that the G field in general relativity only partly depends on the matter field dynamics because only its chronogeometricity will depend on the symmetry properties of the matter fields, as Brown and Pooley will argue. And in the full case will be the Minkowski metric in special relativity, where eta really is fully reducible. It's just a codification, as Brown writes, for certain symmetry properties of the matter fields, of the matter field dynamics. So in this case, it's really non-fundamental. Now, the full case is kind of clear cut for them, and for the partial case, for the G field, they are very careful to say that this is that this means anything with regard to ontology, non-fundamentality, and so on and so forth, because it's really just one aspect of the G field, the chronogeometricity that is touched by this dependence relation. But there is another sense in which G is dependent, and that comes from spin-2 theory, from spin-2 gravity. When we derive spin-2 theory, at some point, one will use the following identity, G equals eta plus H, where H is, of course, the new matter field, and it's important to always note that here we really talk about the full deviation. H really represents the full deviation from of eta from G. And then we can interpret this as an ontological reduction of the observable or effective metric field G to eta and H quite explicitly. We can just read off from this equation that we will use at some point in the derivation that this is an ontological reduction. where the idea of an ontological reduction is just something like that the entities at one level are nothing more than a manifestation of entities at a lower level. So G is nothing more than just eta plus H. And you call then G equals eta plus H a bridge law in this reduction. So the dependence statement would be that G depends on eta plus H, depends on eta and H. Now, even the spacetime metric fundamentalist can accept G as in fact ontologically dependent. That means non-fundamental, and eta would be then the fundamental metric. And these two interpretations, the standard interpretation and the spin-2 interpretation, will differ ontologically. In the standard interpretation, you have really G as a fundamental metric field that is in your fundamental ontology. In the spin-2 interpretation, G is actually non-fundamental. It's derivative on the entities eta and H. Fully depends on that. This is a very straightforward reading of spin-2 theory. This could be a very straightforward reading of spin-2 theory. However, there is a problem, namely that as an identity, the bridge law G equals eta plus H merely articulates a symmetric dependence relation that does not sanction any immediate inference to what is fundamental. You can basically also run the whole derivation backwards and can basically, you can not start from Fitz-Pauli and then end up at some point at the full non-linear equations, as I think Niels talked about 2 weeks ago. But you can really just split up G and end up in your new spin-2 view. So the main problem here being, again, for fundamentality, you want to have an asymmetric dependence relation, but we don't get that, at least from what I just said. So here's a new proposal. Combine, basically, the two critiques of the standard view. Again, the respective problems for inferences to non-fundamentality were that on the one hand, you have that the dependence relation of the dynamical approach only helps for fixed fields and chronogeometricity for the G case. And for the spin-2 theory, dependence relations of spin-2 theory, the dependence relation of spin-2 theory is symmetric. Now, if you combine this, you can say that there is a sense in which the spin-2 view separates what is mixed in the G field of standard GR. You have, on the one hand, a fixed spacetime metric part, and on the other hand, a dynamical gravitation part, which is, of course, feasible since gravity is universal. So in other words, there's a sense in which the dependent and independent structures are separable in spin-2 theory. And then the new proposal would be that you have a dynamical spin-2 view. Then H is a new ontologically independent matter field, and eta fully ontologically depends on the symmetry properties of the matter fields, including H, this new field. And hence, on the dynamical view, the dependence relation G equals eta plus H can really not be interpreted anymore as a simple part-whole relation, because eta and H are not independent of each other. Eta fully depends on symmetry properties of the matter fields. Therefore, eta also depends on the symmetry properties of H. And this gives you a non-literal reading of spin-2 theory. So the main claim would be that combining these two threads paves the way to an inferences to non-fundamentality for the G field. And I say more on this then also in the book. And for example, whether you can have additional support for such a claim, because so far we just talked about GR. And my claim is indeed that this would suggest that already in classical GR, you can make a case that the metric field should be properly understood as a non-fundamental entity, the effective metric field. But arguably, you need to say more, I need to say more to sway the skeptic, and I do this mostly via explanatory coherence. Taking in the dynamical approach gives, as I argue, more coherence to your explanation. You can also talk about quantitative versus qualitative parsimony of what kinds of posits ontologically you accept. But for now, let me just also stress that the analysis of fundamentality as independence, as ontological independence, gives you already a hint that you should look at a unified perspective, basically. You should really take into account all of physics. And this is what I mostly then draw on to give additional support to this view. So since fundamentality is, as independence is implicitly about the dependence relations to all other entities, this unified perspective is really kind of evident. It's evident that you would need this because you want to talk about all these kinds of dependence relations. So you take into account the broader context of physics, and then via such continuity conditions from other parts of physics, you can hopefully then make a better case for this interpretation. However, there are, of course, also quite a few qualifications that you need to take into account, and that Niels, for example, also I think has talked about. So the main qualifications being that spin-2 theory and GR are not strictly equivalent, essentially because spin-2 theory cannot accommodate all solutions of GR. I guess the standard claim would be that it can only get you the globally hyperbolic ones. And arguably, the theories, in the book, I say that arguably the theories are at least empirically equivalent with respect to the well-behaved solutions relevant for describing our universe. But yeah, maybe you also want to push back on that. I would say that the results obtained for spin-2 theory and interpreting spin-2 theory are also relevant when you look at GR, because at least you have quite a few empirically significant solutions where you can actually transfer this reasoning. But if at the end there is an empirical empirical inequivalence here, then this would of course also be nice to know, nice to see, because then you can actually distinguish between the two theories, of course. I will now not so much talk about these kinds of qualifications because they obviously exist, but I want to move on to what Niels and others have kind of put as more philosophical critique, put forward as more philosophical critique. And here, in this paper from 2023, the central issue they make out is presented as a dilemma. So either the view of the metric field as a mere stand-in for self-coupling spin-2 field in flat spacetime is physically incomplete insofar as it requires recourse to GR, after all, or it leads to an absurd multiplication of alternative viewpoints on GR. Now, let me take the two horns separately so reply to the first horn here, too strict. I think it is too strict to regard what counts as permissible in such derivations. So essentially, my point is here, what kind of recourse to GR is problematic after all? It is certainly an issue if you're not able to conceptualize an essential posit. That would be a problem, I guess. And but I don't think that this is happening here. I think it's really also how I read the paper is it's more about the problem that there are many available energy momentum tensors, and you basically have to choose which one is the relevant one, which one gives you actually will give you GR. And for this problem, I'm less convinced that this is actually putting pressure on the proposal, because such a recourse to GR, if you would call this a recourse to GR, may just be understood as a shortcut basically to empirical adequacy. After all, we want to explain this world. We want to have a picture that takes into account what the world is actually like. And it is this world that picks out a specific energy momentum tensor. So I'm not so much worried here about the derivation, that there are certain choices to be made. At the end, it's about this world and it's about empirical adequacy. And if you know from GR that certain energy momentum tensors are ruled out due to empirical adequacy, keeping empirical adequacy, then fine. Why not use this knowledge? So using this prior knowledge in the context of discovering spin-2 theory seems to be just a shortcut to empirical adequacy. Especially if you are more interested in painting a metaphysical picture, of course. The derivation, of course, may be less impressive, but that's something else, I would say. Then the second horn, which is again that it leads to an absurd multiplication of alternative viewpoints on GR. So I would say, yes, it's of course true that you have some underdetermination going on when you could say you split the G field. So you have many different ways of splitting this up. But remember how I kind of phrased this splitting. It was about separating the dependent and independent aspects here. And the proposal to answer to this second horn is then basically that this is just the best systematization where you can actually fully split and fully separate the dependent and independent parts. Therefore, this specific split that I'm talking about is, in a sense, privileged. It is, however, true, of course, that more, as I said, more kind of support from outside, just discussing GR and classical spin-2 theory would be nice to have and can be had to some extent, at least, from a quantum perspective, and I agree with them on that. Then very recently, Niels has had new interesting remarks, amongst others, again, on this more like philosophical packaging of the dynamical spin-2 view I was proposing. And so here's the first quote. So there is both ambiguity, Niels writes, in what the decisive figures behind the approach have stated about its concrete conceptualization and a lack of consensus concerning the conceptual import of the approach in philosophical discussions. And he then lists the following. On one hand, epistemological takes on which the particle physics approach provides yet another means of arriving at the field equations. Then we have intertheoretical takes, he says. Here, the particle physics approach, so this meaning always the spin-2 approach, of course, either shows the inevitability of GR under controlled generalization or demonstrates a theoretical reduction of GR. And then thirdly, you have the ontological takes, for example, process ontology, where you have a genuine interaction picture as he describes it, or you have what he calls a design ontology, which, as far as I understood it, is taking basically certain ingredients that make the world. So this is kind of the idea behind this design ontology picture, that you take certain ingredients and make up the world, which is very closely, which he really relates closely to this God metaphor again. And then his main claim is the following: the ontological readings, these two, are either unattractive, as in the case of the standard ontological reduction claim, or the process ontology claim, or are better seen to collapse into epistemological readings after all, which is apparently the case for the design ontology proposal. And therefore, I am, on his interpretation, not fully consistent, which I am kind of, I see a point there. Not fully consistent, for instance, at moments, Salimkhani seems to claim ordinary ontological reduction with a bridge law, which seems to look as if he was claiming ontological reduction in some context of special relativity, general relativity. Why I ultimately think that he commits heavily to a design ontology stance is his focus on the so-called spin-2 derivation, and the claim how GR arises thereby from consistency. Okay, so here are a few admittedly preliminary thoughts on this. First of all, I very much appreciate Niels' attempt at clarifying what indeed is not always perfectly coherent. For now, I mainly want to push back a bit on one point, that is that I heavily base my argument on the derivation specifically. I do start with the derivation in the book, for example, and I do think it's very interesting and fruitful, and helps to understand what's going on there. But as I view it, I do not base my ontological claims on it. I definitely agree that this can get quite tricky. The argumentative strategy, as I see it, also of today, is rather saying that we should not just work with the formalism or the derivation, because they tend to blur what is of key interest, and that is dependence relations. The argumentative strategy focuses on dependence relations because the formalism is opaque with respect to the question whether eta is dependent or independent. And as argued, the derivation cannot provide an asymmetric dependence relation between the two views, and thus cannot establish fundamentality claims. So the argumentative strategy is really not focusing on the formalism, not focusing on the derivation itself, but I think it is only by philosophical interpretation, namely you have the dynamical interpretation, and by explication, namely fundamentality as independence, and hence related to a unified perspective and so on, that we can actually establish these ontological claims I then make. So I don't think that this really, maybe I'm not a design ontologist, I don't know. Maybe I am, but there is a way to do this that doesn't collapse into epistemology, basically, or what Niels was pointing out as an epistemological way of talking about spin 2 theory. But I again want to say that this is quite important. How I view the situation, that it's really not about the derivation. It's really not about the formalism in the sense of you really just read off your ontology from the equations, but that you look at explanations, that you look at explanatory coherence, that the dynamical view improves on the explanatory coherence of the spin 2 view and vice versa. And that this gives you the best fit also with regards to the dependence and independence of your entities that you posit. Okay. To conclude, according to a dynamical spin 2 view, general relativity supports spacetime metric non-fundamentalism. The directions, the direction of the dependence relations or the dependence relations themselves, I think, cannot be read off the equations and should not be read off the equations or the derivation, for that matter. Determining the fundamentals actually requires philosophical interpretation, and that is because the non-philosophical take on this, the literal, the formalist take on this, will likely paint over the hidden, the implicit dependence relations, and then lead to redundancies, which may not be innocent because of the consistency that you want to have when you talk about the fundamentals, basically. Yeah, thank you very much.
Great, thank you so much. So we have plenty of time for questions. So I'll encourage people to type questions in the Q&A or to just raise their hands, and I can give you all the go ahead to ask the questions yourselves. But maybe I will start with a question. So I'm a physicist, so I very much approach things from that end. And it was interesting to me that you were mentioning how trying to read off dependencies from equations, which is, very much the field in which we play in as physicists, theorists especially, how we can't read off the fundamentality. But does this mean as physicists that we often work in a form that we're agnostic to the true formalism, or are we kind of making our jobs harder for ourselves until we get to clarify it by, like you mentioned, invoking outside knowledge from, say, a more quantum gravity theory or something that we hadn't been considering yet in the set of equations we're currently playing with?
Yeah, thanks. It's a very good question. I'm not entirely sure. I think first answer will be there are different basically different ways to approach this, different aims you have. So it makes sense for many things as a physicist to really look at the fundamental equations, of course. It could be interesting to consider that maybe you miss something when you just do that. But I'm not in any way suggesting that you should now do what I do, of course, but maybe sometimes this can just trigger new interesting ideas or something. But I'm more addressing really the philosophy of physics community here, because it is very common, as I see it, that people just take their favorite theory and just say, what is the ontology of that theory? What is the fundamental ontology of that theory? And I think that gets very tricky because of what I said. It just means that, for example, in the spin 2 case, you will I don't see how you could arrive at the conclusion that eta is dependent on something and should therefore not be taken into account when you look at the fundamental ontology of something. So did I miss anything? Sorry.
No, that was great. Thank you so much. Jacob also has a question. Jacob, go ahead.
Hi, thanks so much, Delilah. And Kian, it was a great talk. I apologize, my Zoom connection cut out for a few minutes in the middle, so if this question was addressed, please accept my apologies. Big fan of your work for a long time. When I teach GR, so I teach the grad GR course. In fact, I think Delilah took GR for me many years ago. So Delilah knows that when I introduce GR, I take a very spin-2 oriented perspective. I classify the different representations of the Poincare group. We talk about how integer spin particles naturally give rise to bosonic fields. We talk about long-range interactions. We classify the different kinds of field theories, and we arrive at the Fierz-Pauli representation of GR in the weak field approximation as a prelude to getting into GR. So this is your work very much resonates with in a lot of ways with the way that I think about and teach GR. But I do have a couple of questions. So one is, and again, I apologize if I missed if this was discussed. But when I think about the metric field, I think of it as a gauge degree of freedom, right? We have, this notion of gauge invariance, diffeomorphism invariance in GR, and so we tend to, after introducing the formalism, we then jump to talking about what are the gauge invariant features of the theory, things like causal structure, curvature, and things that can be directly observed by by local observers in spacetime. And then I guess it's just a little hard for me to see how to think about the fundamentality of either the metric or of the H field, right? I mean, any observer can switch to local inertial reference frame in which H disappears. The metric tensor, that its form is frame dependent. And there's a sense in which once you have the causal structure of spacetime and you have a representation of the curvature of spacetime, any metric that realizes that causal structure and curvature is just as good as any other metric. So it becomes a little difficult. So the way the way I motivate the spin 2 approach is just to say, if you're looking at small perturbations, small gravitational perturbations, and you want to think about how they could be described quantum mechanically, they're going to be spin 2. They're going to satisfy certain consistency relations, and from those we can, determine some of the structure of GR. But once we have that structure, it's like we kick the ladder away, and then we just have, full GR, causal structure, curvature, all of the manifestations of those things, physical observables. So I guess my question is, why should we try to talk about ontology at the level of the metric tensor field or this decomposition in the first place? If that makes sense.
Yeah, thanks. Very, very nice. I think it's a very good question and absolutely makes sense. I think it also gets into the area that Niels is trying to push back a bit on what I've proposed. I And I have to admit that I'm also reconsidering because of such criticism this whether I just want to say this is kind of dependent on a certain view of what fundamentality just means, and if you think about it in the way I presented, then you will end up at having this choice whether you accept something as fundamental that mixes dependent and independent properties, which is coming from this independence notion, not really an option, or whether you kind of try to separate this, but then I'm not entirely sure whether you fully lose the kind of information that is absolute. I completely agree, at the center of physics behind it. I wouldn't want that, but I need to think about this. So on the one hand, I could just say, well, this is dependent on this fundamentality notion. On the other hand, there might be more to it. It's also very much still, I think, as far as I read the literature, debated what others think about this gauge or consistency issues and so on and so forth. How this really can be addressed in a fully satisfying way. So I'm afraid I have to for now say I very much get your concern there, and I will think more about it. But from this perspective of really fundamentality that I kind of put forward today, is it seems as if it doesn't seem that you have really another choice, but it depends on certain and potentially from another point of view very severe assumptions regarding that you actually privilege a certain split of the G field, which runs obviously, or you could think that this runs against key insights from physics, but I'm not claiming that this is this kind of privilege, right? It's not, the split is not in any way picking a reference frame, I hope. But you may think that no, it is actually, and I have to think more about this. Yeah.
Yeah, I worry about it because, of course,
Yeah.
right, if you change coordinate systems, the H field is going to change, right? And that doesn't happen with other kinds of fields. If I change coordinate systems,
Yeah.
The values taken by the Klein-Gordon field, they of course take their values at different locations, but I can make the H field disappear, right, in a particular choice of coordinate system, at least at any point. But I'm connected with this, and I apologize, but this is closely connected with my question. There's a general methodological strategy that one takes in modern physics. We have some very complicated theory that is in some ways calculationally intractable. We're trying to probe its structure. We don't know exactly what form it takes, and so we begin by looking at its perturbative sector. Right. This is a strategy that you see in string theory. You start with strings, even though we don't think it's a theory of strings anymore. You see this if you're trying to understand QCD, right? We start with the perturbative sector with weakly coupled degrees of freedom, where we can do some calculations. We can access perturbation theory. We can look at the structure, and then we can figure out the consistency conditions that the perturbative structure has to satisfy, and from this we can try to infer what's going on in a deeper non-perturbative theory that may be inaccessible to perturbation theory and may look qualitatively quite different from the perturbative sector. So we see this strategy employed over and over again, where the perturbative sector is like the tip of the tiger's tail, and then we climb up the tiger's tail to the tiger. And again, when I teach GR, this is the view I take toward the spin 2 approach, right? We're accessing the perturbative sector of the theory to figure out what are the consistency conditions the theory has to satisfy. but the goal is to arrive at a theory that is a deeper theory in which the perturbative sector, is really not um, fully capturing the ontology. It's just sort of like the tip of the spear. Um, and the second thing I just wanted to say was one reason why the causal structure and is so important um, is when you want to ask questions like how do signals move around in space-time? How do we talk about probability distributions for particles in space-time? Um, like, what do those things depend on? I can't put a probability distribution in the location of a particle along a time-like direction. I can put a probability distribution in the location of a particle along a space-like direction. Um, I can, if I want to talk about sending signals, right, which are the idea of signal locality is really central now to how we think about the structure of quantum mechanics. All of these things, they don't really depend on G or H; they depend on causal structure. Um, and Yeah, so I guess one of my other questions about your talk, and this is a little less well formed, is how do we think about the decomposition of G into eta plus H when it comes to questions like how we put probabilities on spacetime, when we talk about signal transmission in spacetime? It's like not clear how any of that is like. So yeah, my apologies. This is a little bit more amorphous, but what I would say is it would give me a better handle on what we mean by the ontology of the metric field if I could understand how a particular decomposition was related to questions about probability and signal transmission. Maybe that's a sharper way to put it. It's more of a question that way, not a criticism.
No, it's thanks. That is very interesting. I won't have the answer now, but that's something I definitely want to think about now. I agree. So maybe to reframe what I presented a bit. So you could look at this from the following perspective. There is this standard view that in GR the metric field is really fundamental, and then you have lots of problems with the fundamentality or non-fundamentality of space-time maybe afterwards, related to that, maybe sometimes not related to that. And you have various reasons to think nowadays that space-time, the metric, is likely non-fundamental in one way or the other. And that is usually based on highly speculative physics. And I'm now kind of looking into very much established physics, GR, and trying to see how this can play out there. So how this kind of option of something like the metric field being non-fundamental can reappear in such an established theory like GR, and put pressure on this view that there is something completely new happening maybe in quantum gravity, or that you have a different kind of conflict of dependence and independence of posits than usually understood. So maybe it's not so much about GR and quantum mechanics, but it's more like about special relativity and quantum mechanics in a more refined way, understanding the problem basically. But I definitely do see that there might be additional points coming in and then saying, well, but at this and that point, there is another problem that I'm now introducing. Yeah, I have to think more about this. Thanks.
Great. And so if there's one more quick question, we can take that if anyone has one. I'll take a moment, let anyone raise their hand. Oh. Okay, it looks like Jacob is the only one with one more question. So short question, please.
It's a short follow-up question. Thanks, Delilah. Yeah, so I just to maybe sharpen my question a little bit. One could take the view that you have a background space-time characterized by eta, by the Minkowski metric, with H as a propagating degree of freedom, propagating field on that background space-time. If you were to do that, your inclination might be to say that the causal structure comes from eta, and H is just one of many kinds of fields propagating on that background spacetime. And then if you were to ask questions like, what are the sorts of probability distributions? Like I said, I would put on various kinds of matter on spacetime. As I said, probability distributions are assigned on space-like hypersurfaces, not on time-like ones. So you might think that we should be talking about probability distributions at the level of eta, and so forth. But I think this would be mistaken, right? I mean, we know that we want to use the full metric tensor G to pick out which hypersurfaces are going to be space-like and which ones are going to be time-like. And that's going to have all these downstream implications for how we think about probability and, like I said, causal structure and signal transmission and signal locality. So this makes me a little bit. This is, I guess, one reason I'm a little suspicious that we should think about eta as propagating on a background Minkowski spacetime, right? And I'm just wondering if you could maybe help me understand why that inclination is. It's just an inclination, right? It's not a well-formed view, but maybe you can help me understand why that inclination might be misguided. Do you see what I mean? Do you see what I'm asking?
Thanks. Yeah. Thanks. Yeah. So in a sense, this is just. So when I heard this kind of light cone structure remark before, I was always quite quick in saying, well, actually, what I'm trying to say is that you never had eta in a sense. Eta is just a codification of the empirical fact as a really a brute fact that matter fields behave Lorentzian or are Poincare invariant. But I begin to see that this is kind of a bit quick, because I would still have to say give a story of how you then relate, for example, like constructor, as you correctly said, to which metric on a formal level, which metric defines it, and so on and so forth. So yeah.
All right. It sounds like there's a lot more to be discussed offline, especially maybe Jacob and Kian can have some in-depth discussions. Thank you so much all for attending. Thank you, Kian, for giving us such a thought-provoking talk. And we will see you all next week for same time, same place, the next foundation seminar. Thanks for joining us.
Thank you so much for having me.